So I was working at a time at Hughes Aircraft. By the way, I applied for a job at Bell Labs and they didn't give me a job. So so it was the best thing they did for me. Unbeknownst to me at the time. But anyway, so at Hughes, I was actually working on radiation-hardened circuits for space, but I came across this, all these conferences. I was aware of Kang's work, Kang and NC, and the industry, basically it was not holding the charge. And I think because they used a tunnel oxide, it was just too thin. It allowed direct tunneling, but it also allowed reverse tunneling. So on the other hand was EEPROM with 1,000 angstrom SiO2 that held charge forever, and a million years at room temperature. So really, from what I remember, this is 1975, 76, everybody was trying to find an erasable EEPROM that didn't need a quartz window and didn't need 15 minutes under a UV light. And I was driving to a conference with my wife and our little daughter, and I to Colorado. And in the middle of driving, this was a 2-hour drive, I came about this idea, basically what I call the not too thin, not too thick, Goldilocks. Just right. I figured would be somewhere between 5 and 15 nanometer, 150 angstroms, 50 to 150 angstroms. And I'd known from my PhD work at Princeton about Fowler Northern tunneling that at that time very few people had known about. And I knew that Fowler Northern tunneling could work at 1,000 angstrom, but would require 200 volts. And so if I cut it down by, from 1,000 to 100 angstroms, that would mean 20 volts instead of 200 volts. And so when I got back home, Hughes allowed me to do really, we had a pilot line and I could do whatever I wanted. So I took created some floating gate capacitors with a polysilicon floating gate and a control capacitor on top of that. And had a very, very small area that I etched a thicker oxide to grow inside the very thin oxide, anywhere from this range. And the first experiment, it programmed beautifully and erased beautifully, but erased not as well as it programmed, but it held its charge really for indefinitely at 200 degrees, solid as a rock, flat-bound voltage didn't change. So I realized that I was also, when erasing through reverse Fowler-Northern tunneling, I was also injecting charge from the control gate into the floating gate. So I went downstairs to our production people, and this was still an aluminum gate production line, and they had this oxide with 1,000 angstrom oxide with 200 angstrom nitride. I said, can you do this for me on this device, on this floating gate? And the nitride basically gave me that blocking that I needed on the other side. So I went to my boss, I said, look, I'm working on red hot circuits. I know this has nothing to do with what Hughes is doing, but this could be very important. And he agreed, and we started working on this. And the most important thing really out of that is that I spent the next 2 years really developing the understanding, the basic physics of thin oxides, conduction, trapping, breakdown, and out of that came also the limited endurance that comes from trapping deep traps, creating deep traps for tunnel electrons, trapping those electrons, window closure, and that's how you end up with limited endurance. And that was fundamental, basically. I remember 1976, going to 100 angstrom SiO2 was heresy. I mean, it was very unstable, even at 1,000 angstroms. It was not really, the world was still a bipolar world. MOS was still embryonic. To propose going to 100 angstrom, people were, but it was not enough. You really needed to make that a practical device, a practical EEPROM. I needed the smallest possible area of thin oxide so that I would avoid pinholes and have the right coupling ratio between the control gate and the substrate to have most of the field fall across that thin oxide. And again, that blocking dielectric was another very important. And that combination is really what I filed that patent in 1976. And that was the first practical EEPROM we produced to use CMOS EEPROM 8 kilobit that was plug compatible with Intel's 2708, but didn't use ultraviolet light. But Hughes was not really interested in production, if anything, that didn't go into space satellites or spy satellites. But it was a fantastic learning ground.